So great. Now we have all of the ingredients. We have our Markov decision process, which allows us to make actions. We understand how rewards happen. But the important thing here is how to make the best decision, not to evaluate, whether a decision is good or not, right? So how do we select over all of the possible decisions that we could make? So that's the idea of an optimal decision, right? And we can do this by thinking of optimal value functions, right? So we've already defined V of S. We're just going to define an optimal one, right? So this is pretty easy to understand. It's just going to be the maximum state value function over all particular policies that we could create, okay? So for all the policies that we could substantiate, we're going to find the one that leads to the maximum value. Okay, we're going to call this the optimal policy. Okay, we can do the same for the Q function, right? The Q function here is going to be Q star. It's going to be predicated over, again, the state and the action, and we're just going to define it as the maximum amount of value that I can get by taking any particular actions from this state following a particular policy. Okay, so we can then say these optimal functions specify the best performance that we can get in an MDP, and we can say, given this particular quantity here, if we can find that we can solve the MDP, because when we know the optimal value function, we can derive the policy in a very straightforward manner. So let's take a look at what this would look like. Here's the optimum value function for the student MDP, and you can just check this out to make sure it's done properly. And you can get an idea of how to intuitively look at this. Like if we start from the final part, what's the optimum way that we could get to this final terminus state? Well, obviously I would have to take the study arc here and get my plus 10 rewards. So that means the optimum way to do that is at this particular state, choose to go and derive an immediate reward of plus 10 here. That would be the best possible action that we can take, and that would lead us to a immediate reward for this node of plus 10, right? And then working backward from here, if I was working in this node, C2, what's the best possible way that I could get the highest optimum value? And you can see what I'm going to do. I'm obviously not going to go to sleep, which would get me to the final state with no reward, but instead go to study, and that study would allow me to propagate this minus 10, this plus 10 with the immediate reward of minus 2 and arrive at my maximum value of plus 8, okay? So you can see where we're going from this. We can recursively calculate this backwards. Okay, so to define an optimum policy then is to basically define some partial ordering over all the possible policies that we can make. And this is a really crucial slide, so just make sure you remember this, okay? Where we have, just like we saw in concept learning, the idea of a partial ordering, where we're going to say, one policy pi is better than a policy pi prime if for all of the possible states, right, every single state, I can find a value function for the state that's either equal or greater to the value function under another policy, pi prime, okay? And there's a theorem, a really important one for MDPs, that says that there is actually, very nicely, an optimal policy, this pi star, that is always going to be better or equal to all of the other policies, okay? So this type of partial ordering does exist. We're going to able to find a policy that's actually optimal, and it doesn't, and that's really nice because it basically says that, I don't have to follow one type of policy for part of the process and another policy on the other hand for another part of the network, okay? There is one single policy that, a multitude of policies that are all optimal, and all of those optimal policies achieve the best optimal value function for all of the states, right? And that also means that it achieves the optimal value function, meaning that we always take the most appropriate decision to reach the highest amount of rewards. So there may be more than one policy that does this. You can think about why. For example, if I'm in a particular state here, S, and I have another state S prime, and there might be more than one way to reach that state, then taking any of these actions would correspond to having the same policy, the same reward. Sorry, not same policy. Okay, so we're going to find this optimum policy, like we said, by maximizing Q star over all of the possible ones, right? We're going to say a particular action is going to be the right one to take if it maximizes our Q value for that particular state for all of the actions, right? And otherwise, we are simply not going to take that transition. So this is going to end up being a deterministic optimal policy, right? So this is in the case where we don't have any actions that lead to the same maximal value, right? If we have multiple actions that lead to the same maximal value, then we could take either one, any of those actions with equal probability, right? So once we know this Q star, right, we immediately have the optimal policy because we can use this case example to tell us basically, well, if that particular action gives us the maximum value, just let it set it as the policy that we're going to do, right? And so you can probably see where we're going with this, right? We can see exactly what we're supposed to do at every state within our MDP, right? So as you would have surmised, if we started in C1, the most proper thing to do is not get distracted, study -2, study -2, and then get our +10 reward, and then we're done with the day and we can go to sleep, right? If we end up, however, starting from Instagram and browsing Instagram, the best thing to do is to go back to study right away and then go from there directly rather than waste time browsing Instagram and incurring a negative reward every time going through here, okay? So that's the whole idea of the best optimal student, and for the student MDP, the action value function here. Now just note that the diagram is not quite equivalent to some of the previous ones here because the rewards now are on the arcs. So for example, this particular node here, we can browse to get an immediate reward of -1 when leaving this state, or we can leave this state by taking the study route. That incurs a little bit more cognitive load, so it's going to cost us -2 in this case, okay? And you can see that also here, our reward of 0 for sleeping doesn't take any work, but it certainly takes work to study, so -2 over here.